Hello everyone. In the previous video we have discussed about solutions to system of linear equations and pseudo-inverse. In this video we will be discussing about eigenvalues, eigenvectors and diagonalization. So eigenvalues and eigenvectors. Consider a square matrix A which is of dimension n cross n. Consider Ax is equal to lambda x. This can be written as A minus lambda I into x is equal to 0. So we are interested in solutions to the null space of this equation, and here the lambda is also the variable. So we would like to solve an equation which is the determinant of a minus lambda I is equal to 0 in order to obtain the solutions for the null space of a minus lambda I into x is equal to 0. So determinant is equal to 0 indicates that there are dependent vectors in a minus lambda I matrix. So that indicates that there are solutions in the null space. So we are interested in finding out the lambda value which will result in determinant of a minus lambda I is equal to 0. So once we obtain the eigenvalues, we can obtain the eigenvectors by finding the independent vectors of the null space of a minus lambda I matrix. So vectors from null space of a minus lambda I will form the eigenvectors. So if lambda is equal to 0, then eigenvectors come from the null space of the matrix A, because then the equation becomes Ax is equal to 0, and Ax is equal to 0 is a system of equations where the solutions come from the null space of the matrix A. So if the rank of A is k, then there are n minus k dependent vectors that span the null space. So if you have a lambda is equal to 0 as one of the eigenvalue, then, and if the rank of the matrix is k, then there are n minus k dependent vectors. So all these dependent vectors will become the eigenvectors of the matrix A minus lambda I. So that is one special case when lambda is equal to 0. In all other cases, we are all interested in obtaining solutions for a minus lambda I into x is equal to 0. So there are some of the useful properties of eigenvalues and eigenvectors. So sum of the n eigenvalues equal to the sum of the n diagonal entries in a matrix. So if you have a matrix A, the sum of the diagonal elements would be equal to sum of the eigenvalues. Determinant of a matrix is the product of eigenvalues. And third property is eigenvalues are on the main diagonal when A is triangular. So when A is triangular or when A is a diagonal matrix, the eigenvalues are always on the diagonal. Eigenvalues are on the diagonal elements. Okay, and let us see an example of why we need to know the eigenvalues and what is the physical interpretation of it. So what is the use of eigenvalues and eigenvectors? Let us see with an example. Take this matrix. So this is a diagonal matrix, and the eigenvalues are the diagonal elements as it is a diagonal matrix. So, and the eigenvectors are 1 0 and 0 1. So let us see how this particular matrix A would transform vectors. So consider this example. We have a vectors which are taken from the circle, which are spanning a circle, which is shown here as green dots, and each of these dot when transformed, or each of these green vectors which when transformed by the matrix A would be turned into an ellipse, would turn into a point on the ellipse. So a circle is being converted into ellipse. What is happening here? This particular matrix A has eigenvalues 5 by 4 and 3 by 4, and therefore since they are unequal in weight, so it is expanding in one particular direction, all these vectors. So since eigenvector of one of the eigenvector is 1 0, so here for lambda 1 is equal to 5 by 4 we have 1 0, so it is expanding more in the direction of 1 0 and it is kind of shrinking. So both these vector 1 0 and 0 1 forms the major and minor axis of this ellipse, and in this way it will transform any data points into it will transform the data points, and it will change the way they are appearing when we visualize them. So let us see some more examples. So the first example we have seen already. So this is how it changes. Let us take a different example and see how, in what direction the ellipse major and minor axis are. So the second example is something as shown here. Here the lambda 1 is negative and lambda 2 is positive, and lambda 2 is bigger than lambda 1. So what happens is, since lambda 1 is negative, so and it's small in value, so if you see the eigenvectors are minus 1 by root 2 and 1 by root 2, and the second eigenvector is 1 by root 2 and 1 by root 2. So since the first eigenvector is kind of lying in the second quadrant, which is left side of the axis, so left and topmost in the axis, so our minor axis would be aligned with the aligned in this particular direction of the vector. As you can see in this figure, the ellipse, the minor axis is directing the orthogonal vector of is directing towards the second quadrant, and the other eigenvector, which is 1 by root 2 and 1 by root 2, has a bigger eigenvalue, so and it is lying in the first quadrant. So there is an expansion of the ellipse major axis is directed towards the that particular eigenvector. So the bigger axis is 1 by root 2 1 by root 2, and the smaller minor axis is minus 1 by root 2 and 1 by root 2. And let us take another example. So here it's a dependent vectors. So since it's a dependent vector, one of the eigenvalue is 0. So if you see the eigenvectors of these particular eigenvalues, we have minus 0.9 and 0.45 and minus 0.71 and minus 0.71. So one is lying in the third quadrant, the first one is lying in the second quadrant. So but the thing is, the magnitude of the eigenvalue is 0 for the first eigenvector, so it will not have any length for the minor axis, whereas for the second the value is bigger. So this is how it looks like. So let me show it once again. As you can see here, there is no expansion in the direction of first eigenvector because its eigenvalue is 0, whereas the second eigenvector has a sufficient magnitude, so it's forming a line instead of ellipse. So these are three cases which illustrates the usefulness of eigenvalues and eigenvectors.